Let's dive into Reed-Solomon codes, the error correction scheme you've probably used without knowing it. Reed-Solomon codes add redundancy blocks to your data, enabling recovery from transmission errors and storage corruption. First, let's understand the basic structure of an RS code. An RS code is specified as RS of n, k with s-bit symbols. The total code word length n equals 2 to the power s minus 1. The message length k equals n minus 2t, where t is the error correction capability. For example, 255 rupees, 223 with 8-bit symbols is commonly used in CD-ROMs and DVDs. This code has 223 data symbols and 32 parity symbols, allowing correction of up to 16 symbol errors. The generator polynomial is the heart of RS encoding. The generator polynomial is the product of two t consecutive powers of alpha, a primitive element in the Galois field. Alpha is a primitive element of the Galois field GF2 to the s, which you can think of like a special algebraic structure for finite field arithmetic. Think of the Galois field as a circular structure where alpha generates all non-zero elements through successive powers. Encoding is straightforward polynomial multiplication. The code word polynomial c of x equals the generator polynomial times the information polynomial. For systematic codes, you append the remainder of dividing x to the 2t times I of x by g of x to your message. In systematic encoding, the original message appears unchanged with parity symbols appended at the end. Decoding involves three main steps to recover the original data. The received polynomial r of x equals the transmitted code word plus an error polynomial e of x. First, calculate the syndrome by taking r of x modulo the generator polynomial. Second, use the syndrome to find the error locator polynomial. Third, calculate the error magnitudes and correct the received data. The decoding pipeline flows from syndrome calculation to error location to correction. The syndrome tells us if and where errors occurred. The syndrome s of x is the remainder when dividing r of x by g of x. If the syndrome is 0, no errors are detected, and we're done. A non-zero syndrome encodes both the positions and magnitudes of errors. The error locator polynomial identifies where errors occurred. L of x is the product of terms x minus alpha to the ei, where ei are the error locations. Finding the roots of L of x tells us exactly which symbols are corrupted. The roots of the error locator polynomial correspond to the positions of corrupted symbols in the code word. Once we know where errors are, we calculate their magnitudes. The error magnitude yi is calculated using the received polynomial evaluated at the error location. Finally, subtract the calculated error values from the received data to recover the original message. RS codes excel at correcting burst errors, which is why they're used in storage. A burst error corrupts consecutive symbols, common in scratched CDs or damaged sectors on disk. Since each symbol is s bits, correcting one symbol error actually fixes up to s consecutive bit errors. RS codes can be implemented in hardware or software with trade-offs. Hardware implementations use linear feedback shift registers for fast parallel processing. Software implementations are more flexible and easier to debug, but slower. Both need efficient Galois field arithmetic, typically using lookup tables for multiplication. Let's recap the key concepts of Reed-Solomon codes. RS codes add two t parity symbols to correct up to t symbol errors anywhere in the code word. The generator polynomial, built from Galois field elements, defines the code structure. Decoding involves calculating syndromes, finding error locations, and computing magnitudes. RS codes are excellent for burst errors, making them essential in storage systems and digital communications.